In this video, we're going to learn how to do Lewis structures for compounds in which the central atom has what's called an expanded octet. Larger atoms in the third period and below have d orbitals. For example, let's consider sulfur. So sulfur's electron configuration is 1s2, 2s2, 2p6, 3s2, 3p4. Now sulfur also has this 3d subshell, but it doesn't have any electrons in it. Likewise, its 3p subshell isn't filled. Because it has this 3d subshell, it actually has space to accommodate extra electrons. And so sulfur can actually have up to 12 electrons in a Lewis structure. That's what's called an expanded octet. Anything in the second period, for example, carbon, nitrogen, oxygen, fluorine, can only accommodate 8 electrons in their valence shells. And so in Lewis structures containing these elements, you won't find them having more than 8 electrons around them if they are the central atoms, or ever. They can't accommodate more than 8 electrons. Phosphorus, sulfur, chlorine, and larger elements can. So let's try a sample structure. So let's start with SO3 minus, and then I'll do ClO2 minus afterward. First, we count the number of valence electrons, just like we do. The first several steps are going to be the same for any Lewis structure. We can go to the periodic table, and we can see over here that sulfur has 6 valence electrons, just like oxygen has 6 valence electrons. So I'm just going to write a 6 up here. Oops, don't have that much space. Oh, I'm going to write it. Let me bring this down a little bit. So I have 6 up here for oxygen, 6 up here for sulfur. I have 3 oxygens, so that means I have a total of 18 valence electrons attributable to oxygens, and then I just have 1 sulfur, so I have 6 here. And then remember, I have the 2 minus, so that means I have 2 extra electrons, and if I add these together, I have a total of 6 plus 18, which is 24 plus 2, 26 valence electrons total. And I'll do it over here for this atom too. I'll do it for the structure just since we're up here. So 6 electrons for the oxygens. And if I look over here at chlorine, I have 7 electrons for chlorine. I have 2 oxygens, so that's 12. I have 1 chlorine, so that's 7. And then I have plus 1 electron for the 1 minus charge. And so here total, I have 7 plus 12, so 19 plus 1 equals 20 total electrons. Central atom is going to be the least electronegative. Well, we know that oxygen is the second most electronegative atom on the periodic table. And so the central atoms, in this case, it's just going to be the atom that is an oxygen. It's going to be sulfur here, and it's going to be chlorine here. We don't even need to look at the periodic table, but in case you wanted to, remember the atom furthest to the left and furthest toward the bottom is going to be the least electronegative. Least electronegative has to be the central atom. So here now I'm going to draw my central atoms with single bonds to all peripheral atoms. So I have 3 oxygens in, this is sulfite, and I have 2 oxygens in, this is called chlorite. Right now I count the number of electrons in bonds, 1, 2, 3. So it's going to be 6 over here, electrons in bonds. I said I was going to do these structures separately, but you might as well do them together. It requires minimal effort, right? So here I have 2, 4 electrons in bonds for chlorite. And I started with 26 in this first structure. So if I want to determine the total number of electrons, I can just do 26 minus the 6 up here. And I have 20 electrons remaining for sulfite. Likewise here, I have what? I started with 20. Oops. Started with 20. Now I have 4 in bonds. And so 20 minus 4 gives me 16 electrons left here. Let's copy these. Bring them down. And now I'm going to give the peripheral atoms electrons until they have 8. So I have 3 oxygens here. I have 20 electrons left to give. Each oxygen has 2 electrons here. Notice that it's just oxygens with single bonds, so they're equivalent. And so each of these needs 6 more electrons. So it has a total of 8. And I'm just going to give all 3 of them 6 each. And so now 6 plus 6 plus 6 gives me 18 electrons used up. And that means that, 20 minus 18, I have 2 electrons remaining. All of my oxygens are filled, so I have to give the 2 remaining electrons to sulfur. In the chloride structure, same thing. I'm going to give each oxygen 6 electrons, so it has a total of 8. And that's a total of 6 times 2. That's 12 electrons used up. That leaves me 4 electrons, and I'm just going to give these remaining 4 electrons to chlorine. And now if I look at both of these structures, I would normally just count how many electrons each atom has. And, I know that each of these oxygens has 8, right? I just did that. I have 8. I have 1 bond and then 3 lone pairs on each of the oxygens. And so all of them have 8. How much does sulfur have? Sulfur has 2, 4, 6 electrons in bonds, 6 bonding electrons and 2 non-bonding electrons. So here sulfur also has 8 electrons. Likewise, chlorine here on the left structure has 2, 4 non-bonding electrons and then 2, 4 bonding electrons. So it also has 8 electrons. And we might be tempted to stop and just say, okay, well, all atoms have 8 electrons. Great. Let's leave it there and call it a day. For these larger elements, they can actually accommodate more electrons in their valence shells. And so instead of obeying the simple octet rule, in which all atoms except hydrogen want 8 electrons when forming compounds, these atoms have what are called expanded octets. So now there's an expanded octet rule that says that all atoms in the 3rd period or higher want to feel neutral. And I put feel in quotes because what atoms really feel, right? They're not feelings. How can an atom feel neutral? Well, it can feel neutral if it quote unquote feels like it has just as many electrons as it does in its neutral state. So it wants to feel as though it hasn't lost any of its valence electrons. Well, let's consider electrons and bonds. Let's just consider, I have this space down here because I want to do some work, but let's just consider generic atom A. And let's say generic atom A has single bonds to generic atom, I won't call it B just because B is boron. Let's say generic atom E. It has a electron. Recall that there are 2 electrons in each of the bonds, right? So I can redraw one of these bonds just to focus in on it. 2 electrons between these 2 atoms. And then lone pair. The lone pair electrons, atom A doesn't have to share with anything. So it quote unquote feels both of these electrons as belonging to it. Feels like both of these electrons belong to it. However, these 2 bonding electrons are being shared with E. And so here, if we're going to give an even split between E and A, we'll say that at any given period of time, A has 1 and then E has the other. So for this one, it only feels like it has 1. Right? Feels. Like 1 units. Right? There are 2 electrons in the bond, right? We attribute the atom as having those 2 electrons, but it's sharing, right? It doesn't have all these electrons to itself. And so when determining how much or how many electrons an atom feels like it has, we say that bonding electrons only account for half, right? So if I have 2 bonding electrons, atom A feels like it has 1. And so let's just determine how many electrons atom A feels like it has. So it has 2 for the non-bonding, plus 1 for this bond over here, plus another 1 for this bond over here. So atom A feels like it has 4. As much as atoms can feel. Well, all elements want to feel like they have just as many electrons in the structure as they have valence electrons. And what does that mean? Well, let's do a Let's do a simple exercise here. So phosphorus, sulfur, chlorine, all in the same period. If we go to our periodic table, you can see that phosphorus has 5 valence electrons, sulfur has 6, and chlorine has 7. So let's write down the number of valence electrons in this new table. So number of valence electrons, phosphorus has 5, sulfur has 6, and then chlorine has 7 valence electrons. The expanded octet rule says that the number of bonds, not number of bonding electrons, number of bonds, plus the number of non-bonding electrons should equal the number of valence electrons for a given atom. What does that mean? Well, let's think of possible combinations. Let's think of the combination where all of these elements are maxed out in the number of bonds to them. So these are the central atoms. We have phosphorus, sulfur, and chlorine as a central atom. Phosphorus can max out to where it has 5 bonds. Going back up to this equation, well, if it has 5 bonds, no non-bonding electrons, that gives me 5 plus 0 equals number of valence electrons. Phosphorus has 5 valence electrons, so it's fine with that. Which means that sulfur can max out with 6 bonds, and chlorine can max out with 7 bonds. In other words, the maximum number of bonds that one of these large atoms can form is equal to the number of valence electrons. Well, that's just one combination. What if we have some lone pairs? Well, what if, let's say we give phosphorus 1 lone pair. So it has 2 non-bonding electrons, 1 lone pair, right? Here's a lone pair, right? That's a lone pair. Lone pair has 2 electrons, and those are non-bonding. So I'm just going to abbreviate these NB. So 2 non-bonding electrons plus what? Has to be 3 bonds. So here, 2 non-bonding electrons plus 3 bonds gives me a total of 5. So phosphorus can also form 3 bonds and have 1 lone pair. In another case, let's say I have 4 non-bonding electrons or 2 lone pairs. Well then, phosphorus can only form 1 bond. I've written these as non-bonding electrons because this is an absolute electron count, right? Realistically, the terminology I'm more likely to use is lone pairs. And for each lone pair, abbreviated LP, you just do simple LP without the periods too. There are 2 non-bonding electrons, so think in terms of number of lone pairs and number of bonds. Here, let's say we have 1 lone pair and 3 bonds, or 2 lone pairs and 1 bond. Remember, 2 electrons per lone pair. Now let's consider sulfur. Sulfur can form 6 bonds, or it can have 1 lone pair. That's 2 electrons. Then it can also have 4 bonds. Or what if it has 2 lone pairs? And let's see, 6 bonds. So 2 lone pairs is 4. And then 1 bond. I messed up somewhere, didn't I? 2, so that's 4, and then 2, right? Here that's 2, and that's 4. That gives 6. No. Two lone pairs, 2 bonds. See, now I got confused. Okay, let's go back and do it the same way that I was doing it for phosphorus. Because here, let's say I have 2 non-bonding and 4 bonds. Okay, good. That's 2 plus 4 equals 6, according to this equation. And here, let's say I have 4 non-bonding. I can only have an even number of non-bonding electrons. If I have an odd number of non-bonding electrons, then everything goes nuts, right? And then 4 plus 2 equals 6. And let's say I have just 6 non-bonding electrons plus 0 bonds. Am I going to have this? No, that won't work. So combinations for sulfur include it can have 6 bonds, it can have 2 non-bonding electrons and 4 bonds, or 4 non-bonding electrons and 2 bonds. What about chlorine? Chlorine can form 7 bonds, or if it has 2 non-bonding electrons, so 1 lone pair, must have 5 bonds. What about 2 lone pairs, which is 4 non-bonding electrons? Well, then it can have 3 bonds. And now what if I give chlorine 6 non-bonding electrons? It can still have 1 bond. Or do you need to memorize these? No, not necessarily. It's much easier if you just know this equation and if you know this expanded octet rule, that all atoms in third period or higher want to feel neutral, which means that the number of bonds plus the number of non-bonding electrons equals the number of valence electrons. And so now if we go back here, let's consider sulfur. Well, sulfur feels like it has what? It may seem very complicated the way I just did it, but it's pretty easy to determine how many electrons an atom feels like it has. So just considering the central atom, sulfur feels like it has 1, 2 non-bonding electrons, 3, 4, 5 for the bonds. So notice I'm just drawing a little slash through each of the bonds, and then 1, 2 for each of the non-bonding electrons, and I determined that sulfur feels like it has 5. Well, it wants to feel like it has 6. So what can I do? I can take a lone pair from one of these oxygens, and I can draw a double bond here. And just draw an S. Now it's a double bond to this oxygen, right? Single bonds to these ones because I didn't modify those at all. And then it already had a lone pair there, right? So now let's count. How many does sulfur feel like it has? So 1, 2 for the non-bonding, 3, 4, 5, 6 for the bonding. Now sulfur feels like it has 6. And so this is the correct structure. Let's go over to chlorite, chlorine and chlorite. So chlorine in this structure feels like it has 1, 2, 3, 4, 5, 6. How many does it want? It wants to feel like it has 7. And so now same thing I did in the last one. I'm just going to take a lone pair from one of the oxygens, doesn't matter which one, left or right. And I'm going to draw a double bond. And so now I have Cl. One, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6. How many does chlorine feel like it has? Feels like it has 1, 2, 3, 4, 5, 6, 7. And it wants to feel like it has 7. So this is the correct structure for chloride. Let's do one more, just standalone, starting from the very top. Let's do hypochlorite, which is ClO minus. If we go to our periodic table, we know that chlorine has 7 valence electrons, oxygen has 6. Well, there's only 1 of each, so it goes 6 and 7. And then we also have 1 for the minus charge. So total, we have 14. So number of valence electrons equals 14. So that's 14 E minus. That, of course, is step 1. Step 2 is determine the central atom. Well, it's 2 atoms, so we don't really have a central atom. But if we wanted to denote one, Chlorine is less electronegative than oxygen, so we'll treat chlorine as a central atom. Step 3, draw our preliminary structure. Oops, Cl. With single bonds to all peripheral atoms, and I'm just going to draw this horizontal. ClO. Number of electrons in bonds. So I have 2 electrons in bonds. So that means I have 14 minus 2 electrons remaining equals 12 electrons left. And so now I'll draw a chlorine with my oxygen. And now I just want to allot these remaining electrons to the peripheral atoms first. Well, 2 atoms, but oxygen is the more electronegative one, so that's one I'm going to give electrons to first. It already has 2. It wants 8, so I'm going to give it 1, 2, 3, 4, 5, 6. Now oxygen is maxed out. I use 6, so now I have 12 minus 6, 6 electrons remaining. I'm just going to give 1, 2, 3, 4, 5, 6 electrons to chlorine. All right, now what? Well, if I do the calculation here, chlorine has 2, 4, 6, 8 electrons. Likewise, oxygen has 2, 4, 6, 8 electrons. And they both seem good. But we need to check if chlorine feels like it has 7. So by feeling, we just take the number of electrons in bonds divided by 2, add them to the number of non-bonding. Well, chlorine feels like it has 1, 2, 3, 4, 5, 6, 7. And chlorine wants to feel like it has 7, so it's good there. And let's compare this to the other structure, ClO2. Well, ClO2 look like this. Let's just put them side by side. So this is hypochlorite. This is chlorite. In both cases, chlorine feels like it has 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. In the case of hypochlorite, chlorine obeys the octet rule, in which it has a total of 8 electrons. In the case of chlorite, chlorine has an expanded octet. It has more than 8 electrons in its valence shell. But what about chlorate? I'm just going to draw the structure for chlorate, which is ClO3 minus. You can follow the rules and you can determine the Lewis structure for chlorate, but it looks like this. So it has 3 oxygen atoms. It has double bonds, 2 of the oxygen atoms. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14 non-bonding electrons on oxygens. And then chlorine has 1, 2, 3, 4, 5. So I have to give it 2 non-bonding electrons here. And just like the other structures, it feels like it has 1, 2, 3, 4, 5, 6, 7. And this is called chlorate. Chlorine has an other negatively charged oxyanion that it can form. The oxyanion just means anions when it's bound to oxygen, and that's perchlorate. So hypochlorite is ClO minus, chlorite is ClO2 minus, chlorate is ClO3 minus, so perchlorate is ClO4 minus. And ClO4 minus looks like this. It's a chlorine with a double bond to 3 oxygens, and then a single bond to an oxygen. This oxygen has 3 lone pairs, and these other ones have 2 lone pairs. And we can determine what this chlorine feels like, how many electrons it feels like it has. So it has 1, 2, 3, 4, 5, 6, 7 bonds, and only 7 bonds. And recall that chlorine can form stable structures in which it has a maximum of 7 bonds. So perchlorate is just chlorine maxed out in bonds. That's it.